This episode helps us better understand wireless communications. On top, we are deriving useful engineering formulas for EMF and wave propagation. Received signals on high frequency are weaker than on low frequency, even when transmission power and antenna gains are the same. We know that short electromagnetic waves are suffering more from shadowing and penetration loss. However, there is an additional effect lowering the signal, even on a line-of-sight connection. While explaining, we are deriving useful engineering formulas to calculate received power, power density and field strength. We are feeding the power PTR to a transmit antenna, which is radiating according to its characteristic C, depending from the azimuth and the elevation angle. Its main lobe gain, GTR, is given in relation to the so-called isotropic antenna, which is a theoretical reference that does not exist in reality. Now we are going to a distance r, where we can neglect the near field of the antenna. If the antenna were isotropic, then the so-called Poynting vector S, which is practically the power density, were equal to PTR divided by 4 pi r squared. The denominator equals the surface of the sphere through which the radiated power is flowing evenly distributed. For a real antenna, we need to multiply with its gain GTR, respectively its radiation characteristic C. The multiplication with a defined area perpendicular to S yields the power flowing through that area. In case of free space, we can easily derive the electric field E and the magnetic field H. The power flow as well as the field strength are obviously frequency independent. We keep that in mind. Next, we want to receive our signal with a dipole antenna, and we are wondering how the power is getting from the air into the receiver, which I represent simplified as a resistor. Looking at the energy flow lines in space, we can guess that a part of these lines will somehow reach the receiver. Actually, an antenna has a so-called effective area. For a dipole, it is equal to 0.1305 lambda squared. The RF power flowing through this area is guided by the antenna into the input of the receiver. Unfortunately, this equation depends on the frequency, because the dipole antenna must be adapted to the impedance of the receiver by means of a suitable length, for example half a wavelength. So the effective area of a half-wave dipole becomes smaller as the frequency increases, causing the antenna absorb less power, even though its gain is always the same. Let's go back to our isotropic reference antenna for a moment. It is amazing that even though the isotropic antenna does not exist in reality, its effective area can still be determined using the general theory of diffraction. But no worries, I'm just sharing the result. It is equal to lambda squared divided by 4 pi, or 0.0796 multiplied by lambda squared. The effective area of the isotropic antenna is frequency dependent too, and it is smaller than the one from the dipole. These equations together form the so-called Friis transmission equation for isotropic reception. Multiplied by the receiving antenna's gain, the equation applies to any antenna arrangement. And there it is, the bad news. A shorter wavelength leads to a weaker received signal. On a mobile device that is supposed to receive omnidirectionally, we cannot compensate for this using a directional gain antenna. But there is good news, at least for some cases. On higher frequencies, you can achieve a higher gain on the same antenna size. At a base station, we can use an antenna with higher gain, having the same dimensions, and this way the effect can be compensated. However, in case of the communication between two mobile stations, there is no way. Next, we are rearranging the famous equation because we want to use the frequency instead of the wavelengths, and we logarithm it. With an intermediate step, we adjust the equation to kilometers and megahertz, and we are getting this formula. On the left side is now the difference between received and transmitted power. Here we have the antenna gains in dBi, the distance in kilometers, and the frequency in megahertz. I used it a lot in this form, and you can find Excel tools for it that I provided for download together with previous videos about wave propagation. This is the original publication from 1946 by Harald Fries, who was working with the famous Bell Labs like a number of other pioneers in communications engineering. Knowing the transmit power, frequency and antenna gains, we can use the formula to calculate the received power without having to think about its derivation. The received power became so established that communications engineers are often talking about field strength, just specifying the dBm value of the received signal. This is confusing because the dBm value indicates a power in milliwatt, but not the field strength in volt per meter, and perhaps this is a reason for some misconceptions. Another reason might be that it is hardly possible to measure the electric field directly at high frequencies. You have to do it indirectly via the received power. We can convert received power to the corresponding electric field strength, but no surprise, there is a frequency dependency in the conversion. I chose dB microvolt per meter because it is a common unit of measure. For completeness, here's the formula to calculate the electric field strength in dB microvolt per meter from the distance r, the transmission power and the antenna gain. There are many reasons why you want to convert into other units of measurement. For example, to assess RF exposure, we need the electric field strength in volt per meter and the power flux density in watts per square meter. In case you are interested, I can recommend the video about RF limits on Electronics Unmasked. First, we are de-logarithmizing the equation to get the field strength E in volts per meter. Then we remember the relation between the power flux density, the fields and the impedance of free space to calculate the power flux density S. I would like to briefly mention an interesting equation. The ratio of antenna gains equals the ratio of their effective areas. We are obtaining familiar values using the example for the half-wave dipole and the isotropic antenna. We have seen that the power flow in the receive case is completely different from the transmit case, but the reciprocity theorem still applies. Even if we use different antennas, we can swap the transmitter and receiver, and we are still getting the same transmission attenuation. Remarkable, isn't it? The field strength from a transmitting antenna is frequency independent, while in the receiver case the power is frequency dependent. So we're actually having two problems at higher frequencies. The effective area of the receiving antenna becomes smaller as the frequency increases, and on top electromagnetic waves are suffering more from shading and penetration loss. We received a number of absolutely valid questions about EMF measurements and RF exposures from our followers. I will try to answer them in coming videos, and maybe in addition we should talk more about energy flow near antennas. What do you think? Should we? Now stay tuned and don't forget to support the channel. See you soon in the coming episodes.